In this video, we're going to go over quickly the 5 most common types of exponential or logarithmic mathematical models. Our first model is the exponential growth model, where b is greater than 0. Our exponential decay model, also where b is greater than 0, but notice here that we have a negative in front of our b. The Gaussian model. Fourth, the logistic growth model. And fifth, the logarithmic models for the natural log and the common log. Now, the basic shapes of the graphs of these models are shown in the following figures. So in our first graph here, we have the exponential growth model. Our second graph is the exponential decay model. Our third graph is the Gaussian model. Our first graph on the bottom is the logistic growth model. Our second graph on the bottom is the natural logarithmic model. And the last graph on the bottom is the common logarithmic model. So we're also going to go ahead and look at what exactly an example would be like for an exponential growth model and how we might be able to use this to help us. Now, this table shows the estimates of the world population in millions from 2007 to 2013. So we have a scatter plot of the data shown below as well. So an exponential growth model that approximates this data is given by p equals 6,128 times e raised to the 0.0113t, where p is the population in millions and t equals 7 is going to represent 2007. So it's asking us to compare the values given by the model with the estimates shown in the table. And then according to this model, when will the world population reach 7.6 billion? So the first thing we're going to do is use our model. So we're going to pull up our calculator, and in our calculator, we're going to put our model in the y equals. So 6,128e raised to the 0.0113t, or x. And then what we're going to do is we are going to look at our table. Now, remember that 7 represents 2007. So we want to go all the way down here to 2007. So we go to the 7. And our value for 7 says 6,632. So it's actually very close. And for 2008, it says 6,707.8. So we can go ahead and we can put those values in. Now, if we continue with our table and writing down the remainder of our data, we get our model. Our model are these following numbers. So as we can see with our model, we're very, very close to these estimates, especially in 2013 where we hit the model exactly. So we're very close. So according to this model, we want to know, when will the world population reach 7.6 billion? So what's important is that we know that P, our population, is in millions, and that we're trying to reach 7.6 billion. So we're going to begin by taking our model, which is P equals 6,128 times e raised to the 0.0113t, and we're going to plug in our value. Now, the reason why we have 7,600 instead of 7.6 is because the 7.6 was in billions and p is in millions. So to get 7.6 billion, that would be 7,600 millions. So from here, we want to solve for t. So we're going to begin by dividing both sides by 6,128, which gives us 1.24021. So that's approximately going to be e raised to the 0.0113t. Now from here, we want to get this out of an exponential form and into a logarithmic form, so that way we're able to get the t by itself and out of the exponent. So we're going to take the natural log of each side. We're choosing the natural log because the base of the exponent was e. So now that we have that, we're able to cross out our natural log and our e on our right-hand side, which is going to give us that the natural log of 1.24021 is going to be approximately 0.0113t. From here, if we're trying to solve for t, we can just divide both sides by 0.0113. Then, putting the natural log of 1.24021 divided by 0.0113 into our calculator, we get an approximate value of 19.1. So what that tells us is that in 2019, the population would reach about 7.6 billion according to that model. Let's look at another problem involving exponential growth. In this example, in a research experiment, a population of fruit flies is increased according to the law of exponential growth. And after 2 days, there are 100 flies, and after 4 days, there are 300 flies. So you want to know how many flies there'll be after 5 days. So because we're looking for exponential growth, we'll be using the equation y equals a times e raised to the bt. So we were given the information that after 2 days, there were 100 flies, and after 4 days, there were 300 flies. So we're going to take that starting information of 2 days and 100 flies. So here we have our y value is 100 flies, and the time was 2 days. From here, we're going to get the a by itself, giving us 100 divided by e raised to the 2b. From here, we're now going to take our equation for the 400, or the 4 days and 300 flies, and set that up as 300 equals a times e raised to the 4b. Because we have two variables here, this is how we need to set this up. Now we know what a is. A is 100 divided by e to the 2b. So when we plug that in, we're going to have 300 equals 100 over 2 raised to the, e raised to the 2b times e raised to the 4b. From there, that's going to give us, doing some simplifying, we're going to have 300 equals 100 times e to the 2b. Again, because we have 4 b's here and 2 b's there, 4 minus 2 is 2, and that's where we're left with 2 there. From here, we'll divide both sides by 100, which will give us 3 equals e to the 2b. Then we'll take the natural log of both sides to get the b out of the exponent, leaving us with a natural log of 3 equals 2b. And we want to solve for b, so we're going to divide both sides by 2 to get the b is 1/2 times the natural log of 3. Now that we have an a and a b, we can take our b, which is approximately 0.5493, and we can plug it into a, so we can actually get a's actual value. So here, we're going to take 100 divided by e raised to the second power times 1/2 the natural log of 3. And that's going to give us, when we plug it into our calculator, a is 100 over 3, which is approximately 33.33. So we can plug those into our equation now, because we know that y equals a times e raised to the bt. And our a was 33.3, and our b was 0.5493. It asked us for how many flies there were after 5 days. So we're plugging in the number 5 into our t spot. So now when we plug this into our calculator, we're going to get approximately 520 flies. So after 5 days, there'll be about 520 flies.